Yes. All right, so good morning. This is the chapter of electric potential and capacitance, but the focus we are having in this problem is on potential and electric field linkage. Okay. Now let's read the question first. I have a playlist of electrostatics in my channel. You have around 450 plus uh, solution videos with great explanation given on electrostatics. So don't forget to watch that playlist. Let's read this. Now you have a situation where uh, this is a coordinate axis, x and y. You have electric field which is downward throughout this region. This is 325 voltmeter. It's a uniform electric field going downward in the minus y axis. There are 2 points given in this system. Point number A is at point 2 and point 3, x and y coordinate respectively. Point B is point 4, point 5, the x and y coordinate respectively. And you can see, there is a blue color perpendicular line. The two lines are perpendicular, this and this. What is the question, right? So the question is, you have to find the potential difference between 2 points inside a uniform electric field, right? But the condition is use the blue path, right? So the moment you think in terms of linking potential difference with electric field, the conceptualization is you have to link E with delta V, right? E has to be linked with delta V. Now, if you look into this question, right, we know that E and we're supposed to find delta V. Okay. Now, if I recall all the concepts I've studied in this chapter of electric potential, one of the very important concept which I've learned is this, okay, which is E is equal to minus dv by dx. Okay? You can see a lot of graphical questions in my playlist. The graphical questions will give you an insight on another way to approach the concept, right? So how do you apply concept on a graphical question? It's more visual in nature. You may like it. Go through my playlist on electric potential. Now we know this, right? The electric field is negative of the gradient of the potential, which means if you have to find the electric field, find delta V, dV through a distance, right? So V changes with the distance, and the ratio of the change in V, the delta V, the potential difference, divided by the distance through which it changes, and a negative sign gives you the electric field, right? And of course, electric field is a vector. Very important, right? And and this is another conceptualization that comes to my mind. Can I use vectors to solve this problem? Because I'm being forced to calculate across some paths, right? So I have to go first to this path and then to this path, right? Let's see how vectors come to the rescue to solve such problems. Okay. So if I were to mark this point as a point C, okay, and I say you're moving from A to C first, right? You're moving from A to C. The total distance you move from A to C. So this is minus zero point 0.3. This is minus zero point 0.3. And this is zero point 0.5, right? So what's your total change in the distance across which you have moved, right? Which is what is the dx we are referring to? Okay. So the dx we are referring to, although this is more of instantaneous stuff, but if you have a uniform electric field, it's a ratio, right? It's a ratio of VB minus VA, and the distance you move through VB and VA. Unfortunately, we are not allowed to use this particular vector, right? B to A. This is the distance through which you have moved, which is bringing about the change in potential. But I'm using, instead of using AB, I'm using first this, and then I'm going to use this because the question puts a restriction, use the blue path. All right. So I move from A to B. My answer is the distance CA, right, is equal to, this is 0.5 minus 0.3 is equal to zero point 0.8 meters, right? So this total distance through which I move is 0.8 meters. Also note the fact that if your electric field is downward, on the upper side the potential is higher. As you go down, your potential is going down. Make sense? Maybe there is a charge sheet here, positively charged, which is sending out. So if you move away from a positive charge, the potential decreases, right? The electric field due to a positive charge is away from the charge. So let's assume there is some sheet here which is throwing this, a constant value of electric field, which implies the point C is at higher potential than A. As you go down away from the charge, the sheet here, for example, hypothetically, C is at higher potential than A. So I'm going to calculate VC minus VA using this formula. I know my electric field is 325 and is equal to minus dV, the change in potential, which is VC minus VA, okay, divided by zero point 0.8, right? So my answer is VC, okay, and if I talk about the displacement per se, from this to this, and I want to put a sign to it, I can also write a minus sign here, right, in the displacement because I'm doing it vectorially now, okay? So 325 multiplied by zero point 0.8 is equal to VC minus VA. Now, this is a scalar, remember. This is a scalar, okay? And therefore, if I'm moving from A to C, and my potential here is higher, this is at higher potential, this is at lower potential, okay? And I'm moving from C to A, my distance covered is 0.8. My change in potential is positive, right? So whatever value I get, 325 into zero point 0.8, let's calculate it. 325 into 8 by 10. So 325 into 8, 40, 16, and 20, 8 threes are 24, 26. So what you get here is 260 volt. So as you move from A to C, you gain a potential of 260 volts. Okay, 260 volt is your gain. Now let's move through the line CB. Okay, if you notice, CB is in, so if this was J vector, okay, if this was J vector, the CB vector is what type of vector? Okay, that should be clear in your mind. The CB vector is essentially an I vector. So if I do a E dot dx to calculate delta V, which is scalar, I am going to multiply 1j with I because this is I, right? How much is this? So this is 0.4 and zero point 0.2. So this is 0.6 and all. Okay. And the dx is in I direction. So dx is say 0.6 I and j is 325j. If I multiply an I with the j, what I get is a 0 because the dot product of I dot j is equal to 1 into 1 into cos of 90 degrees. Okay, so this is 0. So across this line, there is no change in the potential for the simple reason that electric field is downward and the dr is here. So when I write this equation, which is a dot product of E dot dr is equal to delta V, this essentially takes care of your signs and whatever is increasing or decreasing, you will automatically get. Because if you're moving from here to here and your potential here is higher and your potential here is lower, this is your dx. This is going to be the direction of your electric field, right? And this is at higher potential. And if you're moving from here to here, you're moving from lower potential to higher potential, resulting in gain of potential, right? So from A to C, I got a gain, and from C to B, I had absolutely nothing. So if I use a blue line, I can get the answer as 260 volt as the potential difference between A and B, because VCB yielded me nothing, right? VCB is equal to 0. So this was for your VAC and your VCB. Let me just write it here. VCB is equal to 0. This part is 0 and this part is 260. The net potential, which is VAC, can be written as VAB is equal to VAC plus VCA is equal to 260 volts gain and 0. Nothing, right? So 260 volt is your answer. So the potential difference between B and A is 260. Also specifying clearly that B is at higher potential than A, because if you're going downwards, the potential, if you see the electric field going down, maybe further down below, the electric potential will be less. Okay, I hope you like this video immensely. This was a straightforward question on the topic of electric potential and the electric field being linked to each other. And the topic is the gradient of potential is called as the electric field. Go and watch my playlist. You will see some graphical questions. Very useful. You will score very well with those concepts and the analysis I've done in my YouTube channel. Thank you very much, guys, for your time today, and wait for my next video. Thanks a lot.